Xiaodong Luo from Oxford, and he's going to talk about state estimation in high-dimensional systems, the method of the ensemble unscented Kalman filter.
Yeah, I guess quite a big long title for you. Good afternoon, everyone. My name is Xiaodong, and actually, so I guess I forgot this title. It's a great honor to for us to present our research work here. And my name is Xiaodong, and I work with my supervisor, Dr. Ali Maraz. So for today's talk, it's actually about, say, state estimation problem in actually large-scale problems. It should not be high-dimensional because actually the problem we are considering is, say, something like millions of say state variables. So for today's talk, first of all, we will state the problem in our study, and actually we will then give a geometric solution, which is actually based on the so-called, say, Bayesian recursive relation, which was just, say, presented in the first talk. And actually, there are some difficulties that prevent us to actually apply BRR to the practical problems. So to tackle this problem, actually, we will first consider some, say, simpler situations, i.e. the BRR, the special case of BRR in linear Gaussian systems. And actually, in this case, it's turned out the BRR is actually equivalent to the, say, Kalman filter. And then we'll then introduce some modifications to the Kalman filter. And the objective to do this is trying to, say, extend the Kalman filter to nonlinear non-Gaussian situations. So actually, among these modifications, we are, for today's talk, we will focus on, say, the so-called ensemble Kalman filter, which at the moment is actually, say, the state-of-art method in the community of data assimilation. And so first, we will, say, give some brief review of the framework of ensemble Kalman filter, and then we will introduce a modified scheme to the ensemble Kalman filter, and we'll make some comparison between the ordinary ensemble Kalman filter and our proposed schemes. Unfortunately, for today's talk, we cannot present, say, the analytic result because it's embarrassingly awkward. Instead, we will actually present some numerical results conducted on a toy model. So first of all, let's look at our problem in study. In our problem, we suppose we have a discrete system model, which write in this way here. M is actually transition operator which mapping, say, the state xk to the next 10 step k plus 1. And here uk is actually the so-called dynamical arrow. And we also impose some, say, observer to measure this dynamical system. So here hk is the, say, observation operator. And of course, it's quite possible that we actually got some observation noise here. So here vk represents, say, the observation arrow. And here yk is the observation we finally got. And theoretically, I think we can use, say, the Bayesian recursive relations to solve this problem. Before we move to that, we first introduce some necessary concepts. I guess most of all actually familiar with these concepts. The first concept is, say, the cumulative set of the observation is actually, say, simply a set of the past observations. And the next concept is, say, the prior PDF of the system state, which denoted in this form. And the third one is the posterior PDF of the system state. Once we got, say, the observation at, say, instant k, then we can update the previous one to the the prior one to the posterior one. And we also need two additional PDFs. The one is the observation PDF. This is actually the, say, the PDF of the observation given system state sk. And the following, we have to define this one. This is a transition probability density, which is actually equal to the, say, PDF of xk given the previous state. So that's it. With these concepts, we can actually divide the whole framework into two steps. The first step is the so-called prediction step. We can use this formula to say make some forecasts. So we can get the so-called predictive or prediction PDF based on this, based on the posterior PDF as the previous 10 step and this the transition PDF. And after we got the prior PDF, once the observation arrives, and we can update the prior one to the posterior one based on the Bayes theory. So this theory is actually very beautiful, but unfortunately in practice there are some difficulties, which includes actually the difficulty in evaluating this integral and this integral. And another difficulty is the high computational cost. So to tackle this problem, let's first consider the special case in the linear Gaussian systems. And so we assume the transition operator M and the observation operator both are linear. And we also assume actually the dynamical arrows and observational arrows U and K follow certain Gaussian distribution. So with this, actually, forgive me. With this, actually, we can reduce the BR to the Kalman filter. So I do apologize because actually I am more familiar with those connections in the community of data simulation. So basically, we call, for example, the prior state in the community data simulation is actually called the background. And if we update these prior states to the posterior one, it is called the analysis. I do apologize for that. Possibly it's quite inconvenient for you in comprehension. So, and corresponding, we can call here this covariance, PKB, the background covariance, and the updated covariance, say the analysis covariance. So this first, let me draw schematic procedures of the Kalman filter. It goes like this. If we have, say, the analysis as 10-step K, and involve this random variable forward, we can make some forecast, so get, say, the prior state or the say background. And once the observation arrives here, and we can update the prior information to the posterior one, and then we can actually involve this information to the next 10 step. In this way, actually, the whole framework is a recursive framework. So we can formalize these procedures in some mathematical formulas. So as the prediction step, actually we can make some forecast based on, say, the posterior state as the previous cycles, and we can get this forecast. And similarly, we can actually propagate, say, the covariance as the previous cycle to the background covariance as the next cycle according to this formula. And actually, in practice, the difficulty lies here, because if the system is a large scale, actually the dimension of this covariance is very large. So if we try to compute the full covariance, it's very time consuming. So the objective is to reduce the computation cost at this step. And you only can move forward. There was another step, the filtering step. So once the observation YK arrives, we can update, say, the prior state by introducing some, say, a linear correction term to the prior state. So we can get, say, the posterior one, and correspondingly, we can actually update, say, the prior, say, error covariance according to this formula. And here, KK is the so-called Kalman gate, and it can be evaluated according to this formula. So in order to, say, apply the Kalman filter to, say, nonlinear, non-Gaussian cases, actually some difficulties. First of all is the nonlinearity, because in practice, most problems actually are nonlinear. So in order to tackle this problem, you have to say normally the common way is to linearize the nonlinear function locally. And an example of this kind of filter is this so-called uncented Kalman filter. And another difficulty is, say, the non-Gaussianarity. So basically, it's actually the error distribution is not exactly Gaussian. So in order to solve this problem, we can actually do some, say, distribution approximation. For example, you can use a series, say, Gaussian distribution to approximate an upstream PDF. So this actually leads to the so-called Gaussian sum Kalman filter. And the final, sorry, it should be not final. And another difficulty is, say, the high computational cost. As we said, if this is a large-scale problem, actually it's very difficult. It's very time-consuming to compute the full covariance matrix. So in order to reduce computation cost, we can actually do some, say, Monte Carlo simulation, or you can say understand this method from another point of view. It's so-called, say, subspace approximation. It's very similar. I mean, the example of this method is the ensemble Kalman filter. So it's very similar to the so-called reduced rank Kalman filter. But in this talk, we actually will focus on this type of Kalman filter. So the next step, the next section is focused on the introduction to the framework of the ensemble Kalman filter. But before me move on, I want to, say, give you some figures to show how large a large-scale problem might be. For example, if in weather forecasting, actually the dimension of the model, or actually the number of the random variables, is up to, say, 100 million or even to a billion. And the number, actually the number of the components in one observation is often up to, say, 1 million or 10 million. So in this case, if we are trying to compute, say, the full covariance matrix, it's really very expensive. So to reduce computation cost, the idea is to use an ensemble of the system state to approximate, say, the system sample mean and the covariance. And so I show you the schematic procedures. And if you remember, if you recall, say, the previous procedures, you can find the difference is here. Here in the previous procedure is actually represented by the mean and the covariance. But in the ensemble Kalman filter, we just use, say, ensemble of the system state, for example, with n system state to represent the whole distribution. And we can evaluate, say, the sample mean and the covariance based on this sample. And actually, the next step is to involve each of the system state forward. So we can get an ensemble of the background. And once the observation arrives, we update the individual member of the ensemble according to the Kalman filter algorithm. So we can get actually an ensemble of the analysis. And we can actually do this further to involve, say, this ensemble to the next, say, 10 step. And in this way, it forms a recursive algorithm. So accordingly, normally we can call this set of system state the background ensemble, and this set of system states the updated system state analysis ensemble. So I'll give you some mathematical formulas to describe these procedures in a more rigorous way. So first of all, we make some forecast of the baseline cost for the system state at time step k-1. So we got actually an ensemble of the system state at time k. And remember that here the number of this ensemble members is n. And then we can actually evaluate the sample mean according to this formula. It's just simple. And actually, for convenience in computation, we can create two square root matrix in this way. Actually, the first square root is actually consists of, say, the difference between the individual member of the background ensemble and the ensemble mean. And the second square root matrix actually consists the projection of the individual ensemble member and the projection of the ensemble mean. And with these two square root matrices, we can compute a set of, say, covariance matrices. And the first one is actually the covariance of the background ensemble. And the second covariance matrix is actually the cross covariance matrix between, say, the ensemble, the background ensemble and its projection. And the last one, I will call it, say, the projection covariance of the, say, background ensemble. And with this covariance, we can actually compute the common gain. Actually, for this step, our objective is to evaluate, say, the sample mean and obtain the common gain, and to prepare for the, say, filtering step. Once we got this information, actually, and with additional information from the, say, observation, we can update, say, the background. Say, first of all, we can update, say, the background ensemble mean to the, say, analysis ensemble mean according to, say, it's very similar to the original common field algorithm according to this formula. And we then update, say, the square root according to some formula, according to this formula. Well, here TK is normally called, say, transform matrix in the literature, but actually its choice is not unique. It's actually a research topic in the community of data estimation, so I do not intend to discuss this topic here. And once we got this, we can actually compute, say, the error covariance based on this formula, if it is necessary. But if our objective is not to obtain this one, actually this step can be omitted. And finally, we can create, say, a new, sorry, it's not new, it can create, say, the analysis ensemble as 10-step K according to this formula. Actually, following this formula, actually the ensemble, the analysis ensemble is actually simply consists of, say, the sample mean plus some, say, scaled column vector of this square root. Here, look at here, the subscript I actually represent, say, the ith column vector of this square root matrix. So we then proceeded to introduce one of our recent works. It's actually a modified scheme to the ordinary ensemble common field. But before we move on, let's consider this problem. Suppose we are, say, given m-dimensional random vector, and its sample mean and the sample covariance are known in advance. And if we involve this random variable through, say, a nonlinear function, so that we got, say, the transformed random variable denoted by y. So what's the sample mean and covariance of the transformed random variable? So to attack this problem, actually, there is a method called, say, the unscented transform. So in this algorithm, in unscented transform, the first step is to create a set of actually specially chosen system state to capture, say, the information of the sample mean and the sample covariance. So first of all, we need to generate a set of specially chosen system state according to this formula. And we'll find, actually, apart from this one, actually these two subset states actually are symmetric about, say, the sample mean. Here, I want to say here, if we try to generate 2L plus 1 system state, one requirement is that here L should be larger than the dimension of the random vector in order to avoid, say, rank deficiency. But we will see, actually, in practice, this requirement is actually impractical. So we'll try to, say, loosen this restriction. But anyway, let's first have a look at this formula to generate a sigma point. Here, lambda is actually a free parameter to choose. If the random variable follows a Gaussian distribution, it can be shown that 1L plus lambda equal to 3 is an optimal choice. So normally we will just put lambda equal to 3 minus L. And then here, we also find that actually there's another, say, subscript I here. It also denotes, say, the ith column vector of this square root matrix. And after we generate the sigma point according to this formula, we further allocate a set of weights to each individual sigma point according to this formula. And so for this one, actually, it's slightly different from the rest. So for actually this weight is corresponding to the sample mean. And for the rest of the sigma points, actually they share the same weight. So after we got this, we can evaluate, say, the sample mean and the sample covariance of the transformed random variable according to this formula. And here, sorry, I think I should put, say, well, this is the nonlinear function. I think I got some, say, notation error here. So here is actually the sample mean of the transformed random variable is the weighted average of the, say, the propagations of the sigma point. And similarly, the covariance of the transformed random variable is also a weighted covariance of this one. But note here, actually we introduce additional term here in order to, say, reduce the approximation error. If we actually expand this nonlinear function into a Taylor series, and we will find actually if we introduce additional term here, it can minimize, say, the approximation error up to, say, the fourth order term. So this purpose introduce additional term here. And in case that the random variable follows the Gaussian distribution, it can be shown that the choice of beta equal to 2 is optimal. And so in our modified scheme to the ensemble Kalman filter, we tried to incorporate, say, the unscented transform into the ordinary ensemble Kalman filter. But as you know, as I mentioned, there's a requirement that the number of the sigma point should be larger than twice the dimension of the random vector. And in practice, I mean, if the random vector is a large scale system state, this requirement is actually impossible to implement. So in order to, say, avoid this problem, I think we have to, say, discard some sigma point and keep the others. So to do this, actually I think we can do this in the suite of, say, the so-called principal components analysis. So let me show you the idea. In general, because the covariance matrix actually is symmetric, so we can decompose it through the, say, singular value decomposition. Now suppose by conducting the SVD on this matrix, we got this form. Here, dk is actually, say, a diagonal matrix consists of, say, the eigenvalues of pKa in a descending. We sort these eigenvalues in descending order, and here ek is, say, the eigenvector matrix of the covariance matrix. After decomposition, we simply, say, single out the first LK leading eigenvector and eigenvalue to form a set of, say, sigma point. So that's the idea. So in many cases, I mean, if actually the system states are highly correlated, and this way can be justified because if the system states are highly correlated, actually the actual dimension, I mean, the fractal dimension of the system states is actually much lower than the, say, degree of freedom of the system state. So in this case, we'll find actually many say, eigenvalues actually are very small. Actually, they are close to 0. So we can do, say, the truncated SVD in this way. We single out, say, the first LK eigenvector and eigenvalues, and we are using them to generate a set of 2 LK plus 1 sigma point. And actually, I didn't cover how to choose this parameter. Actually, it's available in the paper we submitted. So after we generate this set of sigma point, we can actually use it, and we can use this information to, say, specify a set of weight to also And then next we follow, say, the principle of unscented transform to, say, evaluate the, sample mean and the covariance of transformed random variable. So let's first look at, say, the schematical procedures I present here. If we compare, say, this one with the previous one, we'll find actually the difference lies in here. In the previous one, we actually got a set of, say, ensemble state, but in the modified scheme, we will introduce some modification based on, say, the truncated SVD, and also we have to with the objective to incorporate, say, unscented transform into the ensemble common filter. So with this one, actually, if we introduce this component into the framework of the ordinary ensemble common filter, then we can use it to generate a set of, say, sigma point, and then we evolve the set of sigma point forward to get, say, the propagation of the sigma point. And once the observation arrives, we can update the propagations according to the common filter algorithm, and then we can compute, say, the updated sample mean and error covariance, and then with this information we conduct, say, the truncated SVD and the unscented transform again to obtain a new set of sigma point and then propagate them forward. In this way, it's actually a recursive algorithm. So I give you the, say, mathematical formulas. So first of all, we made some. I think it should be chi rather than x. We made a forecast of the sigma point to obtain, say, the propagations of the sigma point, and then we can compute, say, the sample mean of the, say, of the propagation based on the unscented transform. So it's this formula. But we need to further compute, actually, say, the sample mean of the projections of these of the propagated sigma point. With these informations, we then create two, say, square root matrices, just like those in the ordinary ensemble common filter. So, and then next we need to compute, say, the error covariance of the background and the cross covariance and the projection covariance, with the aim to, say, compute the common gain. And actually, the common gain just follows the same formula in the ordinary ensemble common filter. And with the common gain and say, this sample mean of the background, we can just update the sample mean of background according to the same formula. But in our modified scheme, actually, it is necessary to compute, say, the updated, say, error covariance, because we need it to generate the sigma points. Once we got these two, say, measures, we can use them to generate a set of new sigma point based on, say, the previous formula I just introduced. So as I said, I think we cannot, say, present, say, the analytic result in today's talk. We'll just, say, show some numerical results based on a toy model. And here is the form of the model. It is actually a simplified model of, say, a simplified model of the atmospheric dynamics. And here, we know actually this model is defined in a cyclical way. That is, if we got this variable, is actually we define it to be, say, x minus 1 equal to x 39, and x0 equal to x40, and x41 equal to x1, and so on. Actually, we can, say, change, say, the up limit of this subscripts. So it's actually can increase to up to number. So for example, you can increase 14, you can change 14 to say 100 or 1000 and so on. We also using this statistics, the so-called relative Lumen square error, to measure the performance of the filters. Actually, this statistic is the ratio of the distance between our estimation and the true state to the length of the true state. So firstly, for the first figure actually is relative Lumen square error versus the covariance inflation factor data. This parameter is introduced to improve the performance of the filter. So I don't want to explain the meaning of this parameter in this talk, but anyway, you can see actually the behavior of the Lumen square error versus this parameter data is just like a U-turn form. But for the ordinary ensemble Kalman filter, it behaves like this one. It's actually after, if we increase this parameter data, actually is enter into a planar rather than a U-turn behavior. And we think out, say the minimum of the Lumen square error to compare the performance. So for our proposed scheme, actually the minimum of the Lumen square error is actually around say 0.17, but for the ordinary ensemble Kalman filter, its minimum Lumen square error is actually up to 0.2. So in this sense, our proposed algorithm outperforms the ordinary ensemble Kalman filter. To summary, actually, in today's talk, we introduced basically the concept and the framework of the ensemble Kalman filter. We also propose a modified scheme called the ensemble unscented Kalman filter by incorporating the unscented transform. And in the future, I think there's possibly a few things we can do. First, actually, we can we may try to find some fast SVD algorithm in order to reduce the computational cost. The other thing is to possibly explore other aspects of the ensemble unscented Kalman filter, including the stability of the filter and the sensitivity of the filter to some built-in parameters like beta. Actually, in our experiment, we simply put beta to be 2, but of course we can tune this parameter. And there's another free parameter lambda, if you remember, is actually when we create the sigma points, we also simply put L plus lambda equal to 3, but we can also tune this parameter. And finally is the possibility to generate other possibilities to generate sigma points. Actually, in our experiment, we're using the truncated SVD to generate the sigma point, but it's possible. Actually, there's other ways to do this. I think this leads to the end of my talk. Thank you very much.
Any questions?
Yeah.
Can you apply a similar strategy for smoothing and not just for
Filtering, not
Yeah.
moving. We do not do any moving stuff. But in the future,
smoothing?
yes,
Yeah.
smoothing. No, just filtering, not smoothing.
Can you do it?
Can you do it?
Yeah, I think so.
guess
Yeah, I
so,
think
right?
so. Basically, it's still based on the framework of Kalman filter. We can do smoothing stuff, but I didn't do it in my simulation.
Actually, I have a quick question as well. So you mentioned that there's a possibility to do reduced rank covariance matrix
Yes.
parameterization. What would be the advantage of what you're doing compared to that approach?
Yeah, the problem is that if we are going to do reduced rank, actually we're still using the covariance, but not the ensembles.
But you're using just a low rank parameterization of the covariance.
Yes,
It
yes.
seems to me that would be more optimal, actually.
Well, this depends. I mean, I think one of the problems is that, personally, well, you have to say using some, just like the SVD, you have to say using some algorithm to determine the rank in advance. I mean, you have to choose the rank of
Yeah.
your.
But I guess the point is there's no sampling error right there. It's an exact up to the number of
Yeah.
sort of whatever rank of the
in that
approximation
case,
is.
I mean, if your system is nonlinear, then if you
Yeah.
actually, I think the reduced rank common filter cannot handle the nonlinear function directly.
Yeah, but it doesn't need to. You just propagate it through nonlinearity. You sample
Yeah.
that, and then you reduce the rank. Of
Yeah, so that's the difference. I mean, if you propagate, you have to say compute, say the Jacobian matrix of the system, right? For propagation, but
You don't need to do that. You just sample it through in a Gaussian in the same way that you do.
oh, I see. So no, it's not a sampling. I mean, actually, even for the ordinary ensemble common filter, it's actually a determined version. It's not involved sampling. And there's other version. I mean, in the early work about ensemble common filter, they try to sample the distribution of Gaussian, made some samples of the Gaussian distribution, but it turned out that actually the sampling leads to worse result than the say the deterministic version. And if you have a look at this, I mean, suppose here we put k equal to 1, and after that, at the first step, we randomly we draw some samples from the Gaussian distribution. So, but at the next step, we'll see actually at this step, because this part, this transform matrix is deterministic. So this one, after you choosing this one, this part is deterministic. So this one is determined, and so next you'll find this part is also determined, and then you forward this part. Suppose, I mean, in say a perfect model scenario, and actually the say propagation of this system state is also determined.
Yeah.
So it's a determined version of common filter. It's
Sure.
yeah,
I
we
think
don't do sampling.
Okay, I think we should take this offline, but I think
Yeah.
that certainly in the linear case, you can do better than this. You don't need to do sampling.
Yeah,
So
yeah, agree. But I mean, for the linear case, actually the advantage is that if we directly involve this system state forward, then the nonlinearity actually is automatically included in. I mean, included.
But there must
in
be just another way of
yeah,
dealing with
You do not
nonlinearity.
have to linearize the nonlinear system. This is a
Okay.
part I didn't mention.
Other questions? Okay, let's thank the speaker again.
Thank you very much.